So the topic of my presentation is local clustering coefficient based degree centrality. So this is a topic that is in the area of network science that falls under data science. I'm not sure how many of you have background in graph theory, so I'll start with some basic things and then we'll move on from there. Uh, So centrality metrics basically quantify the topological importance of the nodes, so we call vertices in a graph, in a network. So the computation of the centrality metrics can be synchronous or asynchronous. So that means if I want to know the centrality metric for one particular vertex, can I just determine for that vertex or for every other vertices in the graph? So if you want to determine for one vertex and you can do just for that vertex, it's called asynchronous. And even if you want to do for one vertex, you have to compute for all the vertices together, it's called synchronous. And the algorithms out there to determine the centrality metrics could be either based on the global knowledge of the network or the local knowledge. And centrality metrics themselves broadly could be categorized, let me not say, as uh, let me make it big this way so I don't occupy the full screen. As either neighborhood based or shortest path based. So neighborhood based metrics basically take into consideration just the neighbors of a node. That means who are connected to a node. And based on that, they go through some algorithms to quantify how important are the vertices in a network. And the shortest path based approaches take a different direction. So they try to quantify how important is a node based on its presence in the shortest path between any two vertices, or how closer is the vertex to the rest of the vertices in the graph. And among this, the betweenness based approach is very important. It has a lot of practical applications because even in a computer network, you want to find out which nodes, which routers could be overloaded with traffic and could really kind of break down. So you want to compute what's called the betweenness centrality of those routers in a network graph. It's a very widely used and studied metric. Unfortunately, the time complexity of computing between a centrality of the vertices is very high. So even the best algorithms out there have a theta of V cube time complexity. And another thing is, as I mentioned already, the different terminologies. So this needs to be computed synchronously. That means even if I want to compute the between the centrality of one vertex, we cannot find the value just for one vertex. We have to run the algorithm across the entire network using the global knowledge, and we will end up finding the between a centrality of all the vertices in the graph, even if you're not interested in the values for all the vertices. So its computation is typically synchronous in nature. So let me show you a graph, a small graph, and the values for some of the commonly studied centrality metrics. So in this graph, I have 8 vertices, and we have the degree. Degree is basically the number of neighbors of a vertex. For node 0, the number of neighbors is 2, so degree centrality is 2. And for node 1, it has 3 neighbors, so degree is 3, and so on. The eigenvector centrality is also a neighborhood-based centrality metric. It captures the importance of a node not just based on the degree of the node as well as the degree of its neighbors. Unless degree centrality, whose values can be open-ended, could be like as low as 0 and as large as anything, depending on the number of nodes in the graph. Eigenvector centrality values are kind of in a scale of 0 to 1, so that way its values are kind of in a bounded range. So the larger the eigenvector centrality, of course, the larger the degree of the node and the neighbors degree of its neighbors as well. And another metric that we'll kind of use in this topic is the local clustering coefficient. It's basically a measure of the probability with which the neighbors of a node could be connected. And we'll talk more about that as we proceed later. And again, since like it's a probability, its values are also between 0 to 1 in a bounded range. The closeness centrality is basically the sum of the shortest paths from length of the shortest paths from a vertex to the rest of the vertices. and you take the inverse of that sum of the lengths of the shortest path. So that's why it's a fraction. Then betweener centrality is basically the sum of the fractions of the shortest path between any two vertices at a vertex that go through a particular vertex. So I'll show in the next slide how you could calculate betweener centrality, but that's a brute force approach. And there are some algorithmic approaches out there, but they take, as I said, a theta of v cube time. So given a graph here, so this graph here, if you think about node 0 in this graph, nobody would need to go through node 0 for shortest path communication. Even 1 and 2, they can directly communicate. They would not need to go through 0 for shortest path. And the rest of the vertices in the graph also would not go through 0 for shortest path. So the betweener centrality of node 0 is 0. On the other, and likewise for 6 and 7, nobody needs to go through node 6 and 7 for shortest path communication. For the rest of the vertices, so let's say we pick up node 5. So here I just list the pairs that would go through node 5 as part of shortest path communication. So in this graph, you can list out all pairs like 0, 1, 0, 2, 0, 3, then 1, 1, 1, 2, 1, 3, 1, 4. So all possible pairs. But only those pairs that are listed here go through node 5 for shortest path communication. The rest of the possible pairs don't use node 5. So that's why I don't include them. Okay, so here, what I mean by this 1 over 2 is for the pair 0, 6. So if you look at 0, 6 and the node 5, there are two shortest paths between node 0 and 6. One would be like 0, 2, 4, 6 of length 3. Another shortest path of length 3 is 0, 1, 5, 6. So out of the two shortest paths between 0 and 6, one of them go through node 5, that's 0, 1, 5, 6. The other one, 0, 2, 4, 6, does not go through node 5. So this fraction 1 over 2 basically means one of the two shortest paths between nodes 0 and 6 go through node 5. Like that for each pair, possible pair, 0, as I said, 0, 1, 0, 2. 0, 1 is not listed here because 0, 1 does not need to go through node 5. So that's why it's 0. The fraction is 0. For 0, 7, again, there are two shortest paths, 0, 1, 5, 7 or 0, 2, 4, 7, and one of the two shortest paths go through node 5. For the pair 1, 6, there's only one shortest path, 1, 5, 6, and that shortest path goes through node 5. So one of the one shortest path between the pair 1, 6 go through node 5. So like this, for all possible pairs, find those fractions and add up those fractions. That's the betweener centrality of node 5. Like that, you can go through for all the vertices, add up the fractions in which they are they are part of the shortest path, and that will be the betweener centrality of those vertices. So computing this, as you can imagine, the brute force approach is time consuming. So the algorithm breadth first search based. So you run the breadth first search algorithm starting from each vertex and then find the number of shortest paths between any two vertices going to the vertex, and then come to these fractions and add them up. And that's like theta of v cube time complexity. So what we now want to do is, instead of spending that much time, and again, if I want to find the betweener centrality of node 5, I cannot just do it alone because I have to run the breadth first search for all the vertices. Then only I can find out how many shortest paths are there from 0 to 6, how many shortest paths are there from 1 to 3, and so on. So that means you'll end up running the breadth first search with each vertex. So as you do that, you can actually determine the betweener centrality of all the vertices, not only for node 5, you'll end up finding the betweener centrality of all the vertices. So that's why it's a global knowledge based synchronous metric. We have to do it for all the vertices simultaneously. So it's kind of a feature engineering approach we took in this research. So we want to come up with a metric that basically captures the idea behind betweener centrality, but in a more computationally efficient fashion. So among the first thing direction that we took is, okay, can we find the correlation between the existing centrality metrics and see if any other centrality metric, typically the more relatively computationally light means which is more efficient and easy to compute, or strongly correlated between a centrality. So for this graph out here, I'm showing here the plots of the correlation, the degree centrality of the vertices and between centrality, likewise eigenvector centrality with between centrality and so on. So we basically evaluate the correlation coefficient of between centrality with each of the other centrality metrics out there. And we find out that the local clustering coefficient has a reasonably larger correlation coefficient. R square is basically the square of the Pearson's correlation coefficient. So if R square is 0.81, the Pearson's correlation coefficient is close to 0.9. So that's kind of the largest among the four different combinations. And not only for this graph, for several other graphs, we can see the local clustering coefficient to be reasonably strongly correlated between a centrality compared to the other metrics. So this gives us a hint that these could be kind of related, but again, the correlation is not really close to 1 or very high and cannot be guaranteed to be that high for all possible graphs. So we want to do some feature engineering here, in the sense that we want to synthesize or come up with a new metric as a combination of some of the existing metrics, and that would exhibit a stronger correlation between a centrality. So let me now introduce local clustering coefficient in little greater detail here. So as I said, it's a probability that any two neighbors of a vertex are directly connected to each other. So that means if the neighbors of a vertex are directly connected to each other, so let me use this example here. Let's use, say, for example, let's see. Okay. Let's think about node 6. So this is kind of what's called the egocentric network of a node. So the egocentric network of a node is basically the comprises of the neighbors of the node and the edges connecting them. So for example, for node 6, its neighbors are 4, 5, 7, and I have those neighbors as well as the edges connecting them. So if you see for node 6, the neighbors of node 6 are directly connected to each other. So if the neighbors of node 6 want to communicate between them, like 4 wants to communicate with 7, it can directly communicate with 7. It doesn't need to go through node 6. Similarly, 5 to 7 or 4 and 5. So that means if the neighbors of your node are not directly, or if the neighbors of your node are directly connected to each other, they don't need to go through the node for shortest path communication. So in the egocentric for node 6, its local clustering coefficient is 1 because the neighbors of this node 6 are directly connected to each other. So there's a formula that you can use to compute local clustering coefficient actually. It's basically the actual number of links connecting the neighbors of your node divided by the maximum possible number of links connecting the neighbors of your node. In the case of node 6, it's 1 because we have 3 nodes and actually there are 3 links, and for 3 nodes, you need 3 links to connect them. On the other hand, for node 5, if you look at the egocentric network, it looks like this. It has 1, 3, 4, 6, and 7 as neighbors. So 1 is not connected to the other neighbors, as well as even among the other neighbors, 3, 4, 6, 7, it's not really a fully connected graph. So if some of the neighbors of node 5 want to communicate between them, they have to go through node 5. For example, if 1 has to communicate with any of the other neighbors of node 5, it has to go through node 5. So the local clustering coefficient for node 5 is not going to be 1 like node 6. It's going to be a smaller number because the neighbors of node 5 are not directly connected to each other. So again, in the formula is the let me see if I have formula here. It's not here, but basically, as I said, the numerator is the actual number of links connecting the neighbors of your node divided by the total number of links between possible among the neighbors of your node. So among 5 nodes, here you need 5 times 4 divided by 2, 10 links to connect each node directly to the other nodes. But you have only 1, 2, 3, 4 nodes. 4 links. So it's 4 divided by 10. So the local clustering coefficient of node 5 is 4 divided by 10, which is 0.4. So that's a lower number compared to 1. So if the local clustering coefficient of a node is low, then more likely the neighbors of the node are going to go through that node for shortest path communication. And if such a node has a larger degree, that means if such a node with a low local clustering coefficient also has more neighbors, and those neighbors are not directly connected to each other, then more likely those neighbors are going to go through that node for shortest path communication. So this leads us to the synthesis of a new metric called LCC prime DC as the product of the complement of local clustering coefficient, which is like 1 minus LCC. As I said, if LCC is 1, like node 6, then nobody needs to go through node 6 for shortest path communication. On the other hand, if LCC is low, like that of node 5, then several of its neighbors are going to go through node 5 for shortest path communication. So that's why you take the 1 minus of LCC. So LCC is 0, 1 minus 0 is 1 times the degree. So degree, if the degree is larger, that means the node has more neighbors and several of the neighbors are not directly connected to each other. So larger the 1 minus LCC and larger the degree, the product is also going to be larger. So if a node has more neighbors and those neighbors are not directly connected to each other, that means LCC is low, 1 minus LCC is going to be high. That means those neighbors are going to go through that node for shortest path communication. Then we can expect the between centrality of the node also to be high. So that's a very good what do you call principle that we can use here. That is, if the neighbors of a node do not use the nodes for shortest path communication, then the rest of the nodes in the network will also not go through the node for shortest path communication. What I mean by this is this. So if neighbors of node 6, like 4, 5, 7, are not going to use node 6 for shortest path communication, we can't expect 0, 1, 2, and 3 to use node 6 for shortest path communication. On the other hand, if neighbors of a node, like for node 5, if its neighbors are going to use that node 5 for shortest path communication, you can expect the rest of the nodes in the network also to use node 5 for shortest path communication. So that's the idea behind our hypothesis or proposal for coming up with LCC prime DC as a new centrality metric, which is computed as the product of 1 minus LCC times degree. And we claim that this LCC prime DC would exhibit a very strong correlation between a centrality. And computing this LCC prime DC is going to be very easy in terms of computational complexity because both local clustering coefficient and degree can be locally computed with just the local neighborhood knowledge. You don't need the global knowledge of the network. And it can be computed asynchronously. That means if you need the LCC prime DC for just one single node, you can do it by computing the degree of that node as well as its local clustering coefficient. You don't need to compute the LCC or degree values for the rest of the nodes in the network, unlike between a centrality where you have to go through the breadth first search algorithm to find the shortest path from each node to every other node in the network. So this can be computed locally in an asynchronous fashion. So I show here for the same graph the LCC prime DC and the between a centrality values of the vertices, and I rank the vertices in the decreasing order of the betweenness and LCC prime DC values. So the betweenness centrality for node 5 is 5, that's the largest value, and the next largest is 4.33 for vertex 4, and the next largest is 4 for vertex 2, and so on. Similarly, if you rank the vertices based on LCC prime DC, the largest is 3 for vertex 5, and then for vertex 2, it is 2.67, and so on. So the ranking, if you compare these two rankings here, it's almost the same except that instead of 4, 2, it is 2 and 4. Everything else is the same. So this means you could expect a very strong or similar ranking of the vertices based on LCC prime DC compared to the relation to betweenness. So that means if you just want to rank the vertices based on betweenness instead of actually computing the betweenness centrality values, you could as well compute just the LCC prime DC values and rank the vertices, and that would rank, and such a ranking would be very similar or close to the ranking you will get based on betweenness centrality. So here I show actually the computation of LCC, which we went through for a couple of cases. For example, for node 5, it has 5 neighbors, degree is 5. So the actual number of links you will need is 5 times 5 minus 1 over 2, which is 10. And actually they have 4 links like I showed here. So the local clustering coefficient is 4 divided by 10, 0.4. And 1 minus 0.4 is 0.6 times the degree 5. So 0.6 times 5 is 3. So like that, if I'm interested in the LCC prime DC of node 5, I can just do for node 5. I don't need to compute this for every other node of the network. So this way you can compute for all these nodes in an asynchronous fashion. In parallel, you can do this in parallel. as well as just based on local neighborhood knowledge. Similarly, you can, so this is a Spearman's rank-based correlation coefficient approach. I'm not sure how many of you know about this rank-based correlation. So basically, you rank, you determine orderings. Here, I want to order based on smaller to larger values for both the metrics. And accordingly, I come up with a tentative rank, which is basically just from the top to bottom. And then for the final rank, you have, if you have a tie, you break the tie um, by taking average. So for example, three nodes have betweenness of 0. So the tentative ranks are 1, 2, and 3. But the final rank is average of the tentative ranks. The average of 1, 2, and 3 is 2. So all the three nodes get a final rank of 2. If there's no tie, then the final rank is same as tentative rank. So do the same thing for both the metrics. So in the case of LCC prime DC, again, three nodes have LCC prime DC of 0. So the final rank is the average of the tentative rank. And once you get the final rank based on these two metrics, you find the difference between the final rank and then take a square of those differences and sum the square of those differences. So this is a formula. There's 1 minus 6 times the sum of the squares of the differences divided by n times n square minus 1. N is the number of nodes in the graph. So if you plug in all these values, you get 0.98, which is pretty much close to 1. So for this graph here, we can see these two rankings basically. So the correlation coefficient basically quantifies extent of similarity in the rankings. In this case, it's 0.98, the similarity between the two rankings. Similarly, you can also see measure what's called the concordance-based correlation. That means if I take two vertices, say Vi and Vj, if the LCC prime DC of Vi is greater than the LCC prime DC of Vj, and I say the betweenness centrality of Vi is also greater than the betweenness centrality of Vj. So if for a pair LCC prime DC of Vi is greater than Vj, then the other one betweenness is also greater of Vi is also greater than Vj, say concordant. And if it is less than here, it's also less than here, then it's also concordant. On the other hand, if LCC prime of Vi is greater than that of Vj, but the betweenness of Vi is less than that of Vj, then we say the pair is discordant. So we want between these two metrics for any two vertices to be concordant as much as possible. So again, for this graph of 8 vertices, I list down all the possible pairs and find out the number of concordant pairs and number of discordant pairs and take this ratio, which is basically number of concordant pairs minus number of discordant pairs divided by total number of pairs. So in this case, it's 27 concordant pairs are there. Only one pair is discordant, like this pair is discordant. As you can see, the LCC prime DC of vertex 2 is 2.67 greater than 2.5, which is LCC prime DC of vertex 4. But the betweenness centrality of vertex 2 is 4 is less than. So here 2.67, the first number is greater than the second number, but here the first number is less than the second number. So that means that pair is discordant. On the other hand, for everything else, so for example, this 2, 3, 2.67, the LCC prime DC of node 2 is greater than 1, which is LCC prime DC of node 3. Similarly, the betweenness of node 2, 4 is greater than the betweenness of node 3, which is 0.33. So 2.67 greater than 1 and 4 greater than 0.33. So in such cases, we say the pair is concordant. So like that, we find of the 28 pairs, 27 pairs to be concordant, only one pair to be discordant. That means if I want to just compare two vertices and say whether and find out whether the betweenness centrality of Vi will be greater than that of Vj or not, it's sufficient to find the LCC prime DC of the two vertices and compare them. So for example, if I want to know whether betweenness centrality of node 3 will be greater than of node 5 or less than that of node 5, compute the LCC prime DC of nodes 3 and 5. If LCC prime DC of node 3 is greater than node 5, we can also predict with a strong correlation the betweenness centrality of node 3 will also be greater than that of node 5. So this is a local, just pairwise correlation between the two vertices, which you can do with greater prediction accuracy. And this is a global ranking. So both global ranking and local pairwise comparison could be done with a higher good prediction using LCC prime DC. And we also went ahead and calculated the Pearson's correlation coefficient between these two metrics, which is based on this formula where you find the average of the metric values and then take the difference between the individual values minus average, square them up, and then sum of the squares and plug it in this formula, and also take the product of the differences and plug it in this formula, we get to be 0.9675, which is again close to 1. So the correlation coefficients are typically from -1 to 1. They cannot go outside this range. And larger positive, that means there's strong positive correlation between the two metrics. So we went ahead and also said, since the the Pearson's correlation coefficient is high, we kind of did a linear plot between these two metrics, and we see it to be kind of a linear correlation between them. So that means if you know the LCC prime DC of the vertices, we can plug it in this plot and predict the betweeness centrality of those vertices as well. And the prediction, what's called standard error of residuals in this case. So using this linear equation, you plug in the actual LCC prime DC values, and using the slope and the intercept of this equation, we can predict the betweenness values. And we know the actual betweenness values from the betweenness calculations as well. So take again the difference between the actual and predicted, square those differences, called the squares of the residual error, and use this formula, sum of the squares of residual error divided by degrees of freedom. Well, degrees of freedom is basically the number of observations, which is the number of nodes in this case that you're observing for the betweenness centrality, minus the number of model parameters. The slope is the model parameter here, and the intercept could be tuned to 0, so we don't consider that as a model parameter. So the standard error of residuals is basically this formula here and comes to be 0.55. So again, it's a very small quantity. That means the prediction of betweenness centrality is going to be reasonably close to the actual. And you can see that in the numbers here. If the predicted betweenness is negative, it means the actual is more likely to be 0. And 2.33 predict to be 2.9814, predict to be 4.07, 0.33 predict to be 1.3, 4.33 this predict as 3.795, predict as 4.6, and 0, 0 negative predict as 0, negative 0.27. So the predictions are reasonably close to the actual. So we went ahead and did this for several real world networks out there. So real world networks means the actual networks, like for example, it could be an airport network, or it could be a kind of a social network, or a lot of real world networks people use for benchmark studies in this area. And we found out the correlation, these three correlation coefficients of this LCC prime DC versus betweenness, similarly degree versus betweenness, closeness with betweenness, and eigenvector centrality betweenness. And the color coding here is like the more dark green here, that means the numbers are more closer to 1. And if it's less than 0.8, but is above 0.4 or 5, they are shaded light green here. And then if it's less than 0.6, it's colored in yellow. And if it is negative, it's more like pink and dark pink and so on. So you see, it's for LCC prime DC, it's mostly kind of this greenish nature. And degree is kind of next to LCC prime DC. It's kind of strongly correlated between us. But the shortest path centrality metric, closeness centrality, which is the other shortest path centrality metric I listed earlier in the slide, is not that strongly correlated between us. Even though both are shortest path based, betweenness is a measure of the fraction of the shortest path going through a vertex, whereas closeness is a measure of how close is a vertex to the rest of the vertices. So even though both are shortest path based, the underlying phenomena they're trying to capture is different. So we cannot use closeness to kind of rank the betweenness centrality of the nodes. And similarly, the other neighborhood-based metric, eigenvector centrality, is actually the least strongly correlated. It's actually very poorly correlated with betweenness. So that means, and again, this is just based on Pearson's, which is prediction linear correlation, and then the global ranking Spearman's based correlation, and just a pairwise concordance. And with respect to all these three correlation coefficient metrics, we see the LCC prime DC to be strongly correlated with betweenness centrality compared to the other centrality metrics. So that's a significant contribution from us in this area. That means we can use this LCC prime DC as a computationally efficient or light metric to rank nodes based on betweenness, both globally as well as locally, just pairwise or among all the nodes in the network, as well as be used to predict the betweenness centrality of the nodes. And it can be computed in parallel if there are facilities to do parallel computation, which is ideal for autonomous systems. And it requires only global knowledge. So from all different perspectives, it is turning out to be a good metric and as an alternate for the computationally heavy betweenness centrality. Okay. So that's kind of our contribution to this research. With that, I end my presentation. Are there any questions?